let's get talk together, and now I'm going to go over the notebook and see together how it works. So here we have another implementation of the same function. Here the difference is we do the operation that we mentioned before on the broadcasting section, and then remember this gives you a distance matrix, which will be n by n by the dimension of the vectors, and then we multiply, we get the square of every element, and we sum over the axis of the dimension of the vectors, and like that we compute the Euclidean matrix, and let's see, we have it. And here is the implementation we already saw. This one is a bit more complicated, and we're going to go one by one every line of code. So the first thing here, we already saw it on the presentation. The Euclidean distance, instead of computing like this, we write it like a scalar product, and the scalar product we write it like this, and we said that we have a NumPy function to solve to compute any of these terms, and like this we can get a very good NumPy implementation. Okay. Here the most complicated part is the einsum, because dot already we see is we saw a matrix product. Einsum is stands for Einstein summation. That in Einstein summation, this operation x, y, k, y, k, j is equivalent to a sum over the repeated indexes. So we have k and k repeated here twice, and this means that there is a sum implicit there. So these two things are equivalent. And here you have the x and the y, which is exactly in this example, and those are the examples. And those are the indices. And the arrow just means that don't sum over one of these one of the indices. So we have two repeated indices, I and j, but we don't sum over I. We let it as a vector. Okay? We only sum as j. So this operation here will give us an array that is sum over k, which is the dimension of the every row for every row. So we have x summed x, and this is exactly what we need here. We do the same for y. And now, so let's check some examples how this the einsum works. Here we generate some data. This has the same shape of the other one, just n by 3. And here, if we use this array and do the operation that we know, the shape that we described before, the operation, the array is going to be of size 10. It's going to be this thing here. And then this size 10, we want to sum it vectorially, as we saw before. And then we are going to create a new axis in this dimension. And here we sum the whole thing, x2 plus x2 transpose. That x2 transpose is the equivalent of doing MP, a new axis, comma. No? We just take this one and do the transpose. So take it to x2 transpose shape, give us what we want. And then when we sum this one, it gives you a 10 by 10 matrix, which is exactly what we want. Dot, going to go over quickly. It gives you a matrix multiplication And here we can time the operations two equivalent operations. One using zoom, and one using is the same thing, x times x, zoom axis equal 1. And then here we will see why we are using zoom. Is it because zoom is faster than this other operation that is equivalent? And which this is another important point in NumPy. There are different ways of doing the same thing, and it's worth to explore some of them, so you can take the one that is more convenient for you, that uses more less memory or runs in less time. Okay. This is for homework. Is try to understand this one. I'm not going to look at it now. And we have two implementations here, and we're going to time it, and we're going to see which one is faster. And here we're going to check that they give the same result. But this is very important. Oh. Because if it is faster and doesn't give the same result, well, it kind of misses the point. So the first implementation is 1 second, and the other one is 51 milliseconds. Okay, so this one is much faster than the other one. And we're not going to compare it with loops, but because loops doesn't make sense. But for sure, both of them are valid implementations in NumPy, and they are faster than going element by element. Here we check that they are the same. The difference is 10 to the minus 12. And this one you already probably have it. We're going to replace in the other one, in the first implementation, the last line by an ISOM. And here this one is a bit more complicated because it's with three-dimensional objects, but the logic is more or less the same. You zoom over the repeated indexes, and the ones that you want to give as a vector, you just put it here. So here we're only zooming by k, and y and j is kept as a vector, not sum. So we get a finally matrix. So now there are questions. Somebody has questions, you can raise your hands and I will unmute you. Or if somebody prefers to type. Okay, then if it is clear, we can continue. Well, we're going to continue anyway, but tomorrow there is more time. If you have a second look to the notebook and you have new questions that you didn't have today, we can see it on the Q&A. So we go back to the presentation, and today in the afternoon now we are going to come back to the same code we already had, and we're going to use profiling tools in Python to see in more detail, besides what time it gives, how the operations, how much time the operations in our functions take, and also we're going to profile the memory. Later, we're going to see a bit of Numba, a small introduction of Numba. Tomorrow you will have much more. And finally, we will see. Then we have a break, and then we come back to with Dask. So let's go to the profiling. Profiling. Let's open the notebook profiling 01 line profiler, and we start there, and then we see the main profiler. So profiling, here we are going to, so I bring again the two functions that we already know. Profiling is about seeing how much time the code that you're running takes. Normally in more detail, like you can go one line by line. You can see the memory. Sometimes there are errors and you want to debug, and you can use tools for that. Here, what we're going to work is in the time that every operation takes, and later we're going to see the memory that every operation takes. Okay. So we generate some data, and here again, time it is the first profiler. If you have two implementations and you want to know which one is faster, you just use time it, and then you can have an idea. We already knew that Euclidean trick is faster than Euclidean broadcast. But now let's go inside Euclidean trick and see how it behaves. For that, we are going to see first line profiler. Line profiler is a Python tool. You have to install it, pip install, and you get it. And you can run it on the terminal. It's a command line tool. But we have here in NumPy, there is in Jupyter, there is support through magic commands for this command line. And for that we do load extension, line profiler. And now this one will make available the command lprun. Lprun, you can use command exclamation or a question mark, and it will give you the help. So you see how to run it. You do present lprun -f, the name of the functions, -f, another function, the function that you want to profile, and here a code that uses that function. When you call in a code that function, it will go there and will do the profiling. And in practice, it was like this. We do lprun -f Euclidean trick. This is the function we want to profile first, and we run it. This is the data we generate. Okay, this is just the name of the function, and this is a statement that contains the function that we want to run. So when we run it, you see here we get a more detailed information than with time it. The first thing is the unit. We have 10 to the -6 seconds. This is microseconds. And then this is the total time that, if you see here, it matches with what we had already computed. And now those are things that are relevant only for the command line if you run a script with it. And now we can jump to the table. So here it gives you the function and line by line some data. So the first thing is the number of time that this line was run. It was run only once. If you have a for loop, it should appear here in hits many more times. Time is the total time that this function run, and this one a time per hit. So if you run it once, it will be only these two will be the same. If you run it more times, here we have the total time for that function, and here the time per hit, per run. Okay, and then the percent of the total execution. And then here we see that these two they are kind of fast compared to the other one. Most of the calculation time is spent on MPI dot, and on the final line, that is summing the final results. Okay, we can do the same now with the next one, the Euclidean broadcast. And here, so the time is same as we saw before, it's about a second. And we see here that this operation takes much more time than this sum here. But this operation at the end is giving you is giving a array that is n by n by 3. And this one is also sum, but is n by n. So here there is more operations and memory changes in play than another sum like this one. Okay. And the other part is the final sum over the last dimension to compute the Euclidean distance. And, it takes half of the, well, a bit less than half of the other one. And like this, you can see your code line by line. So if you want, if you have if you have a script and you want to run it on the notebook, what you do is you get your script, you put it inside of a function, and then you run it like this. And like that, you don't have to go line by line, checking time it and seeing it's destroying your code. And with this one, you do it in a single run. Okay. There is some question here. I'll go to the, what is the meaning of per hit column of the output? What is the meaning of the per hit column of the output? Is if a line is run many times, let's say that this one is inside of a for loop, the total time here will give you the, because it's the same line, right? The total time this function run, and per hit will be the independent, the time per run. Okay, if you have here for 10 times, it will give you approximately 10 times what it took here, and this one will be about the same time. Okay. Okay. So this is a line profiler. It's a very simple tool. We can add it to our toolbox for the day-to-day Python work. And I will also show you cprofile. The cprofile, you don't have to install it as the other one. It comes already with Python. And in Jupyter, it's available through the command line, the magic command line %prun. So we run it here. And now, just by looking at the output, you can see that it's more detailed and more complicated, because it will give you not only the line at line level, but it will go at function level all the functions that are called in every line. So here you can see things like method NumPy core multi-array math implement array function. Everything of this everything is hidden from us because this is part of the NumPy core. Same here, a lot of strange names. So this one is, as you can suspect, is more relevant for if you are developing libraries, or you want to have control of all the depth of the execution, and the line profiler is more for the quick checking if an implementation or some line is causing bottlenecks in your script. Okay. And here, if we go by columns, the columns are extremely, well, not extremely complicated, but a bit strange to understand. Total time is not really the total time, it's the time that the function takes, your Euclidean function, your function takes without counting calls to other functions. For instance, if in your function there is x plus y, this x plus y is going to, this time is going to be registered here in total time. But if there is a call to another function like sum or dot, that one is not going to be registered here. That one is going to be registered in cumulative time. So this one is the total time, it's actually total time, and this one is the total time without the call to other functions, okay? And per call is cumulative time per call and total time per call is the same as hit. So per every time you run it, and this one would be like the total time, consider the total time that the function runs, the some call runs, if it runs only if it runs more than one time. Okay, you want to check the questions here. Again, my recommendation, if we are starting in for this kind of work, this one can be useful for you. That one is more like advanced. If you have to have the control of everything that your function is running. Okay. Now let's go now and check the memory. Let's go here to this one, memprofiler 02. We open it, and this is not a notebook; it's a script, because memprofiler doesn't have support for Jupyter Notebook. No? And we're going to run it by hand. So we take a terminal. I think I can put it next to, and you can still see. Yeah, I'm already in HPC Python. Well, I'm in profiling, so I can run it. I already have my Python is the same of the kernel. I do Python memprofiler 02. Let's see first what it does, and then we see the details of the code. So here is the same thing, pretty much line by line, but it will give you the increase of memory per line. And that one, this one can be a bit confusing, because right when the function starts, you get 48 megabytes that you may ask where this is coming from. So this is coming from, this is the memory used up to the point that your function starts. So here you have the memory of starting Python itself, the things that you import, or if you declare a variable, all this is going to be here. And from now on will be the memory used by your function, which is what you're interested in. If you go line by line, the first line, it says no memory. Somebody wants to type why there is 0 memory here. There is an assignment, so there has to be some memory. Or raise your hand and I can unmute you. Well, okay, I'm going to reply myself. This one is something similar that we saw here. I think I can do Ctrl+P. Here, that we had some free memory, and the next something that fit there, Python allocated in that place. This is the same that is happening here. Of course, the memory management always is complicated, and things they don't look they are not what they seem. But I think in this case it's that. So when the program starts, it requires some memory that some of them is free. It only was let's say needed for starting the script, and now you have free memory inside. These two lines here, that they do not occupy too much memory, they can be fit there. So you get no increase according to the main profile. Okay. So to this point, you have the same memory you had before. Now we do this one. This here apparently requires much more memory, and it adds 31 megabytes to the execution of the execution of the function. So there are 31 megabytes when you run this one, and at the end there is more or less the same amount, because it comes to be expected. The same size of arrays are produced here, and remember that these two are n by n matrices, and this one is n by 3. No, by the small dimension. Okay, and so it kind of makes sense. It makes sense that these two are consume more memory. I'm going to check the questions. Okay, is it fine? Okay, perfect. Now let's have a look to the other implementation, to NumPy broadcasting. This one I have it on the 03. So we have NumPy broadcast. So we see here the start is more or less the same, because the script will be the same until this point, and the data is the same. Here, this operation takes 1.5 gigabytes. That compared to our previous implementation. Oh, I lost it, actually. Let's put the previous implementation here. The Euclidean trick. Euclidean trick in total, at the end of the function, only use 110 megabytes. And here, this one, we see at this point there are 1.5 gigabytes. And this is something that is very helpful, the mem profiler, that you can see which functions are more demanding memory-wise. This one in total takes 1.6 gigabyte. It's much more than our implementation. So this one is not only slow, it also requires more memory. And actually, the fact that it requires so much memory can justify why it's slower. Okay, and the thing comes from this line that, remember, gives you a line, an array n by n by the dimension of the array. In this case, it's 50, so it should be 2000 by 2000 by 50. Okay, this one needs a lot of operations in memory, and your function end up being slow and using much more memory. Okay. So how you do it is very similar to the other one. You have a function, you import mem profiler. The mem profiler you can install with pip. You get your function, you decorate it with profile. This profile comes with mem profiler, and then you just run it. You do Python the function. Remember, this one there is no Jupyter support, and it will give you the same things. Pretty simple. If you have code that is not in a function, you can quickly wrap it inside of a function, decorate it with profile, and run it, and then you will get all this useful information. Okay? So, questions? Okay, if it is clear, we can continue to the next examples. Otherwise, remember, you can always ask tomorrow in the Q&A. I'm going to put this back here. Okay. Now we talk about before we talk about the Euclidean distant matrix, and now, but we also mentioned that we're going to do it also with the city block. But the city block, the expression is different here. The distance is different. So we cannot apply the same trick, the mathematical trick. And if we cannot apply the mathematical trick, we can go to the broadcast, like Euclidean broadcast. This is a good implementation, but it takes a lot of memory. Maybe, and it's slow, we saw. And maybe it's worth to see other, not go beyond NumPy. So going beyond NumPy, our first stop is going to be Numba. Numba is a just-in-time, it provides a just-in-time compiler that changes your Python code into machine code. It kind of compiles your Python code, and it will be faster. Okay. For Numba does this using the LLVM compiler library. So when you install it, it brings everything that you need. You don't have to do anything. It's just pip install or conda install Numba, and you get everything set up. You can mix it with the NumPy arrays. It's designed to be used with NumPy arrays, since NumPy arrays are the base of most of the numerical calculations with Python. And it brings not only for CPU code, but also brings tools for support for GPUs. So you can write GPU code with Numba. That one you will learn tomorrow, not today. And it runs both in NVIDIA and in AMD hardware. So you have CUDA and ROC. How it works? So you have a function. This is a very simple function. You call, you pass an array. There is some index here, and then you go over the array with a loop, which you already say that is not good, but now I will explain why we're doing like this. And then we sum all the elements of the array, and then we return the sum of all the elements. Okay, so this is a very slow Python code, but to make it Numba, this we only add this thing here, and that's it. This code here, when this function is run the first time, it's going to be, this code is going to be compiled, it's going to be translated, compiled, and there is some binary code that will be in memory, which is this binary, which will be the compiler representation of this function. So the first time that you run it will be a bit slow, but the rest of the times that you run it is going to be quite faster compared to the original Python thing. So this decorator here is the only thing that you have to do. Numba git. Git means just in time. Just in time is because it is compiled when you execute it. And this no Python true equal true that we add here is because there are two ways of compiling compiling Python code with Numba. And one of them, which is this one, no Python true, there are some features of Python that they are not available. In general, when Numba cannot guess the type of the variables, in Python we are used to change types. Something was a string, and now it's an int, and now later it's a float. But with Numba, these features they are not in this kind of compilation. No Python true, they are not allowed. But on the other hand, this way of compiling gives you the best performance, okay, compared to, well, NumPython equal files. And now we're going to go to the notebook and have a look how Numba works. So sorry, we go here to Numba, simple, city block distance matrix, Numba. There are questions? Okay, I'm going to introduce you to the notebook a bit, and then I will leave you some time to play with it. Okay, so we import Numba, and we have 3 implementations. The first one is, it says naive Python implementation. Is we are talking this is city block matrix. We compute it here with loops. We already know this is going to be slow. The next one, we have Numba, and so we use the JIT decorator. Pretty much is the same thing than here. The only difference is for the innermost loop that is doing the. So these two are combining the rows, and this one is doing the city block distance. No, we are using, instead of range, this is what we had here. We are using this Numba function that is p range. That means parallel range, which it allows us to do to compute parallel code. So parallel loops, sorry, just for free. And it takes in account privatization of data when you have reductions, and everything is very simple for the user. Everything is hidden from the user, and you just write that if it is Python. And the next implementation, it does again use Numba, and does again the two loops combining the elements of the rows, but the final the city block function is computed with NumPy, not with this inner loop. Okay, and now please go. I'll give you until 50, and go through the notebook, and then try to understand. Try to understand what's the difference. Why one is faster than the other ones. Python is simple, but the other one, the other two Numba ones, they are not as simple to understand why they have different execution times. Okay, please, if you have questions, type it or raise your hand. Okay, let's discuss the notebook. Oh, sorry, there's a question. City block number 2. Why would you not use number range in both loops? Okay, that's a nice question. I'm going to talk about this first, and then we're going to reply to the question. So first one, we have Python, the very Python version, almost 2 seconds, but that we are expecting that this is slow because of the for loops. That one is fine. The next one is 645 microseconds. Now you see the speed up only for doing just by putting a decorator here and doing the p range. It's almost for free. Tomorrow you will learn with Theo going even further and getting better performance by specializing more your function. And the last one is faster than NumPy, but it's a bit slower than the Numba one. Here, somebody would like to type why? Or raise your hand and I unmute you. Okay. Here, the difference in execution between the two Numba versions is that this one, the for loop, the innermost for loop, the Euclidean, the city block distance, is done explicitly with the for loop, while this one is done with NumPy function. So this NumPy function is probably a C function that I can tell you is not multi-threaded, and here we can see that the speed up. Sorry, it's a C function that is not multi-threaded, and Numba, there is no optimization that Numba can do for it. For Numba, this is just some binary code that it has to run, but there is no optimization. This doesn't have a way to optimize it. In the other hand, this one that has a very explicit construction, like a for loop, Numba knows what to do, and that's the difference in time. That this one is Numba optimized, and this one is not. Okay. Now, the question, the question is the city block Numba 2, the second one. Why would you not use Numba p range in both loops? It's the same as in this one. We only use Numba p range for a single for a single loop, not for all of them. And here we use only for one. The logic behind it is like this one is going to create threads. It's going to unroll it and will create threads. Let's say 24 threads, which is the number of total CPUs in peace-dimed. And if we put the p range in both of them will be creating threads, and then the threads are going to conflict one with the other one. And then what we do is we put it only on the last one, and it will be something like this. When I is equal 0, it enters in the second loop. The second loop is going to run all the threads. It's going to in parallel. They are going to run. When it finishes, it goes to the upper loop, I equal 1, and enters here again and create all the threads. So if all the both at the same time I create threads, all the threads they have to compete with each other, and probably you don't get as good performance as only this one here. Okay. And here is the same. Here we don't use p range here. We only use it in the innermost loop. This loop run, and this one will be always running in parallel. So you always have parallel code running in your function. So we can run this one again. We can do it together. We can open top, And we can see here, so this one, we're running now the Python version is only 100%, only one CPU is being used. But you will see that when it moves to the Numba versions, this one should change to a higher percent. It did not. Okay, I'm sorry about this. I will have a look what is happening and I come back to you later. There are more questions. Replace range by range. It seems to get the same performance here. Why is that? Marlon is asking if range is replaced by range, the performance is the same. Well, we just find out why was that. It's because range is being is not being parallel. Is doing the is running a single in a single thread. I have to look at it why this is happening. Okay, Hannes explains that there is a missing thing here. Let's run again. I'm going to comment the other two to save some time. Okay, now you see the high GPU usage, 2400%. Thank you, Hannes. I'm sorry, I completely forgot about this. So apparently, we need to add parallel equals true. Otherwise, the P range doesn't do anything. Thank you very much, Hannes. I'm sorry. I will put it also in this one. So you can do the same and you have it. And later I update it to the repository. Thank you very much. So I'm going to close here. Okay, great. Okay, now let's see the whole thing well written. Okay, the performance is even worse. Very interesting. Somebody has idea? Maybe there? Okay, I going to have a look. I'm sorry about this, and then I come back to you. Okay. Okay, some of you found an error by adding parallel. Could you please restart the kernel and run it again? So since I didn't try the parallel through for some reason, I have to have a second look and I come back to you about it. Maybe I can find the errors again. Somebody else reported that he got an error running it, but run again and now it's running. Jonathan and Loic are saying that probably there is a lot of context switching during the parallelization, and it's more expensive to do the thing in parallel because you have to be changing from thread to thread. But maybe that's why creating the loads in performance. I will have a look again to that one. And okay, those are the questions. Okay. So now we have it's 2, and now we can take a break 15 minutes, and we come back at a 2:15. Okay. Please type if you have more questions. Type it on the chat. Okay, we're back from the break. So during the break, we had suggestions from some of you. Here we have a suggestion of Jonathan, which is he changed the NumPy range in Numba one function from the innermost to the first one, and that one, so if we run it, is faster than the rest. And the thing, as many of you suggested, can be because of if we run in parallel only the last one, the innermost loop, then there will be a lot of so 2000 by 2000, no, it's 200, no, 200 by 200 times the Python have to create threads, and well, not Python, the Numba code create and destroy threads, and this creating and destroying threads just has a lot of overhead. And thank you, Jonathan. This is a very good point. The other questions for many of you, or I don't know why for not all of you, when running this cell, you got an ugly red message, but this red message is was not, I think it's not an error, at least for me it's not an error. I had the initially wrong kernel, that's why I didn't get it. I had a newer version of Numba by mistake, and for this version it gives an error, sorry, a warning. I think if you run it many times it should disappear, that says that Numba failed in no Python true mode, and this error is just that Numba is falling back to no Python equal false, which is the slower implementation. Since I have the wrong kernel, I didn't see that error. I am going to have a look tonight to it, and then tomorrow in the Q&A we can see a solution. We can see we can explain what's happening, and also maybe some of you will find it too. We can discuss about it. There is a question of Francesco that Theo suggested to reply live. Are you there, Theo?
So yes, I'm here. I suggested to reply live, but I also wrote the answer. So Numba generally uses the LLVM, and so it produces LLVM IR, and it does not compile into C. There is a way to make it compile into C, but in general, it's better to leave it do its thing, because it does all the optimization and uses SIMD, SIMD, and everything. Also, one other thing for the parallel, in general, we will see also tomorrow when we go into more details that when the code is a little bit complicated and Numba cannot see how it can parallelize by itself, it throws you some warnings, which you can dive into more detail with some parallel diagnostics that it gives you if you need. And we will see tomorrow directly through an example that how you use the parallel and how you use the diagnostics, and it tells you directly which point of the code it was able to parallelize and which was not able.
Okay, thank you, Theo.
So it's not always true that, although that you may suggest it, that to run parallel if it cannot understand how the code that's going to be produced is going to be valid. Then it will throw you this warning and it will disable the parallelization for you.
Okay. Questions about it? Okay, let's then have a look. Well, tomorrow with Theo, you will have a look, but in the Q&A we can discuss about all these problems. And now let's go to the last example that is going to be with Dask. Dask is a library that introduces for parallel computing with Python, and it introduces a dynamic task scheduling. And it also has an extends the pandas data frames that we're not going to see in this course, but probably all of you know, and NumPy arrays and Python lists. That extends it to distributed environments and high, so more than a single node, multiple nodes, and with a low, higher than and larger than data larger than memory. And the good thing with Dask is that you can develop your code in your laptop, even if it is with the data that is very large, and then the same code will run in your laptop and will run in NPy with just a couple of lines that you have to change. Okay. So the first thing we're going to see first the dynamic task scheduling. Dynamic task scheduling is done very simple with something, the construction in Dask called Dask delayed. For instance, if you have a code, let's say you have these three functions, and you get x equal function 1 with some arguments, y function 2, some arguments, and then z depends on these two. If you run it in your normal Python code, it would be something like this. You run sequentially this one, then the other one, then the other one. And Dask introduced this delayed that the function, instead of running the function directly, you will wrap it with Dask delayed. You pass the same arguments, but the function is wrapped by what's the Dask delayed. And like this, every of these lines, you're not going to run anything. You're just going to declare a computational graph. So when you run this one, you run this one, this passes immediately. And this one creates a graph that starts with x is passed to function 1, y passed to function 2, and then the result of these two, as you can see here, is passed to function 3 and then to z. And then Dask, when you run this one, we can say z compute, and then you're going to get this when you get they give you the value. Before there is no, excuse me, there is nothing is run, it's just declared. And the things that are not dependent on each other, Dask is smart enough and will run it in parallel if possible. Okay. Also, you can do things like for throughput running. You can create a list of Dask delayed tasks, which are functions. You define it here, and then you do Dask compute, and you run that list, and then Dask will run it, will schedule it in parallel, all of them. And then the scheduler you can choose threads and processes, and well, basically threads and processes. It has other options, but they are more for debugging. And the other part that I say that is an extension of NumPy arrays and Python list and pandas data frame is that Dask has an implementation of each of them that is that with almost all the functions of NumPy and data frame and Python. But they are implemented differently in chunk base by doing the calculation by small parts, by blocks, such that you can run things with data that doesn't fit in memory. And this is very powerful. And then, well, just because of that, and we're going to see some examples now. We're going to start with Dask graphs. we're going to learn a bit first how to compute, to construct graphs. So let's go to the notebook 01 Dask intro, and let's play a bit there. Here in Dask, in the first one, so we import Dask, and we declare that there are two functions. One, you give a number, and I give you the square, and the other one you give the number, and I give you the sum. So if we run, I put here a times leap. So they take more time than they take more time, otherwise we don't see anything. So if we run this one traditionally with normal code, it will take 3 seconds. But if we use the Dask delay to create a computational graph, when we run this one, this passes. You see that there was just a declaration, there is nothing run. And we can visualize the graph. You see here, so Dask will run first the 2 square functions, and then we pass it to x, and then the result is going to be passed to x and y, that will be passed to add, and then you will get set at the end. Okay. And at this point, you don't have the value. If you want to, if you know, if you want to see, if you want to compute set, you have to run set.compute. And here we see that it takes only 2 seconds. Why? Because it ran this one twice, sorry, at the same time. It's 1 second each, but in total it's 1 second. It takes only 1 second instead of 2 because they were run simultaneously. And then they go to add, and add is another second, and then you get 2 seconds. And the very important thing here is that if you remember at the beginning in the morning, the CPU bound and the IO bound functions in Python, that they have a different implementation of the lock. This function is a leap. Since it is not CPU bound, there is no calculation. It's just a call to stop the execution for a certain amount of time. This one is an IO bound function, and it releases the GIL. That allows to them to run at the same time. If this function wouldn't release the GIL, these 2 seconds that we got here, that was not going to happen. Even if the graph is like this, it will take it wouldn't run concurrently. Okay, this is a very important thing. When you create your graphs in your work, in your real work, sometimes you will see, okay, these two, they are not dependent, and but they took the same time as sequentially. What is happening? That can be happening. Okay. And now the rest, there are some questions that are very simple, and I give you some normal Python code, and you have to convert it in Dask delay. And here you can run this one and see the solutions. Okay, it's very simple. Let's give it 5 minutes, maybe a bit less. If you have questions, please raise hand or type. Okay, let's have a look to the questions. So the first one, well, the solution is here. We use delay on the square, and you can use it delay also on the sum. So we can, let's see how it looks like. Oops. So this version looks like this. All these squares are computed first, and then when they are ready, they are added to sum. Somebody did not run did something different. Okay, another option is this. Let's see what happens. We get something like this. It's very ugly, but it's pretty much the same. Here you have something, these two, they're combined in add, and these two are combined in add, this. And the execution is going to be similar, because all these squares, since they are not dependent, they are going to be computed at the same time. And then the add is they're going to be running in add. And the shape of this one is because the add function, the sum function, will take two elements, sum them, whatever it gave, it will sum it to the next, and the result to the next, and so on. So at the end, both are equivalent solutions. Okay. No questions. The next one is pretty much the same thing. It's just written in a different way. We can add Dask delayed to the square function, and to sum. And the last one, again, pretty much the same, but we have an if else. Then if we run this one here, oh, sorry, run the wrong one. It's going to take like 10, 12 seconds. Here you see that some of them are adds and some of them are square. It doesn't matter the order in which they are here, because they are going to be run concurrently. Okay. So here there is a question. So run it. The number of threads, the processor 24. How much time it takes if we use 24 calls, and how much 25? So we have 24 total processor with the hyperthreading undyed. So if we run this thing, let's put y.compute, and we can put the time it here. So here we have 10. Let's see how much it take. No, time it maybe was not. I think time is faster, I suppose. So only 1 second. So we can go up to 24 1 second. And now if we go to more than the number of cores, it's going to get 2 seconds, because Dask is going to, it takes a number of, here by default, takes a number of cores and schedule all these tasks in 24 tasks. So in 24 threads of execution. So, and then since there is another one, the next one is going to run after all these 24 things are done. Okay. Questions? Okay, let's continue and see an example a bit more difficult. Here, let's move now to the notebook 02 exercise city block distance matrix. So we open 02. So this one is a bit more complicated. We're going back to the city block. And we're going to do something different here. So we generate some data. And there is a function in SciPy that's called cdist that if run like this, and you put city block here, will give you the function, it will give you what we want. It's the city block distance matrix. It's already implemented on SciPy. But if we run it, we can look here to top, it runs in a single thread. So it's fast and optimized, but it's a single thread. So maybe we can use Dask and somehow break the execution into chunks and try to run the distance for every of the chunks and then put them together so we can parallelize it. Okay. And this is what we're going to do here in this notebook. You should go through the instructions. Here the code is already divided in chunks. We select 12 chunks because there are 12 CPUs, but you can also try something else like 24 with the hyper-threading or something, whatever you want to try. And what we do is we use this function split, and we take the x and we divide it in 12 parts, in 12 arrays. No? And now we do a loop over all these 12 arrays, and we compute the city block between x and each of the chunks. So we will have oh, I have part of it, spoilers here. We have so part of the matrix, and at the end what we want is to concatenate it together and get the final value, the whole matrix. Okay, so in this exercise, please go to the order of the exercise and try to. Sorry, I opened the solution instead of the exercise. I'm sorry about that. So here, so the chunks are done, but there is no Dask delay. Everything is going to run. It's just going to be worse because it's going to run sequentially plus the chunks. So the exercise is go through the notebooks, and there are things that are wrong, like this one, and try to fix it. Put the Dask delay where it's supposed to be, and then run it and check the times, and the notebook will guide you through the activities. Just read the comments and these notes here. Okay, so I will give you until 50, and then we discuss together. Okay, let's discuss the notebook. I'm going to the solution one. So we run it here, and we see that cdist takes about 3.3 seconds. So we do the division in chunks. And here, to make it delayed, what we have to do is every one of these tasks in this list, we have to use the Dask delay, okay? Visualize it. Now we have a set of tasks that are independent to each other because they just operate in different data. So we continue, and the next part is that we have to delay the concatenate, okay? And this one gives you the final value. We visualize it, and we see this is what we're expecting. All the tasks are run here, and then they are put together in the concatenate, and then finally give us the value that we want, which is the city block distance matrix. Let's time it. We already timed it here. It's almost 1 second. It's 3 times faster than the other implementation that we had. And let's explore a bit. And now we can explore a bit what's happening. And also, well, maybe it's worth to look. I don't know if you look to top, but while it's running, we see here that there is a multi-threading thing happening, and this is actually what we wanted, no? Many threads. And going back to the GIL, this means that the cdist function is releasing the GIL. Is releasing the GIL. Otherwise, they wouldn't have run in parallel. You would have all of them running one after the other one. Okay. There are other ways to run here. Threads, we can use also processes. We can see, we can come here, and we see all the processes. Instead of before, we only had one running in many threads. Now we have many processes. Okay, now they are finished. Oh, no, they haven't. They are still running. I will check the questions. And here, the important thing is that these processes, let's see the final time, how is it? The important thing is that in processes, the data that every process uses is copied. So we have in threads, all the data is shared. That's why there is a GIL. But in processes, the data is copied. So this would be more. We can expect that this more. This is lower than the threaded version because it has a lot of operations in memory. Okay. Then we safely can stop it, and because it's very slow, let's run the thread again to get rid of this orange message. Okay. So now we can check that both give the same solution. They do, and there is a point here that we use a concatenation. Concatenation again is an operation in memory. It must be expensive. No? If we run here this operation, only so we run the part without concatenation, so only the I got the notification. No. Only this part here, we see that it takes 346 milliseconds, which is roughly a third of this. So most of the time, it's not doing computation; it's just inputting together the data, okay, in a single matrix. And here finally, we can do, this is just more about development, a function that you pass the x and the y and the number of chunks that you want, and it will give you back the distance matrix and everything, all the delayed operations and splitting is hidden from the user. So if you have this in a package that you are developing, you define this function, and user will do from your package import this function, and then it runs, and all this parallelization is happening in the background, and everything is hidden. The user just see, okay, I have a function that runs in parallel and gets the city block matrix. Okay. And finally, we check that the function gives the right value. It's very important. So one point here that I put in the conclusion is that it's very important that this function, the one we parallelize, cdist, is not multi-threaded. Because in the first place, if it is multi-threaded, it runs in parallel already, and if it comes from SciPy, probably it will be faster than anything that we can do hastily. But the other point is that we don't want the threads of the Dask delayed execution conflicting with the threads of the function that we are running. So in general, if we do that, we have to take care of putting by hand how many threads each one has to run, if that's possible. This one, in this case, it runs only a single thread, and it's fine. Okay. Other questions? Somebody wants to if you raise hands, we can discuss. Everything is clear? Okay, we can jump to the last notebook. We're going to the 06 this time. That's processes versus threads. And here, maybe somebody can raise the hand and we can discuss, or again, type the answer in the chat. Here we have this, we can do it together. And I will give you a couple of minutes to reply. But we have this function that we saw before. It's a NumPy, sorry, Python, almost Python only function. It has this is NumPy, but the rest is Python. Of course, it has loops, it's very slow. And we want to check in this notebook how Dask behaves with this not truly NumPy function half and half. So we're going to run it. We're going to create some data, not too much because, not too big because this is going to be slow. Okay, let's run here first and see what happens. And in the meanwhile, so it takes 3.2 seconds. In the meanwhile, let's create a graph. This doesn't make too much sense, but the idea is we want to run this thing twice. And in principle, okay, say we want to run it concurrently, both at the same time, because this one runs in a single thread. So we create this Dask, this graph. This graph is one doesn't depend on the other one, so they should in principle run together. And now when we run, so we can run with threads and we can run we see that it takes 6.7 seconds, twice. So there was no parallelization. And if we run with processes instead of threads, it takes this. The question is, are you able to estimate how long it's going to take? And explain your answer. Like if you can type it on the, or raise your hands to discuss, would be great to explain what is happening here. To give you a couple of minutes. Okay, we got an answer from Jonathan, which is exactly what should be happening, right? This function that we are running here is not releasing the GIL. Compare, and then so when you run it sequentially, it takes 3.2 seconds, and then if it doesn't release the GIL, Dask is trying to run it concurrently, but this function is forcing Dask, forcing the threads to run sequentially, one after the other one. And that is exactly what is happening here. Then here you get 6.7 seconds, which is twice, okay? And then why this one is faster than this one? Well, it's because it's using processes. The processes, as we saw before, they copy the memory, and then they do not. So the GIL doesn't affect the GIL. So Python create two processes, both run the function thread safe because there is no shared data, and then like this you can run the two tasks concurrently. So this is something that you have to keep in mind. keep in mind, and sometimes you can select a process over threads. The problem of the processes, which in this case was the fact that the copy memory was what saved the day, because thanks to that we managed to run it concurrently. That can backfire, like before, that if there is a lot of memory involved, then the process may slow down the function because it requires a lot of copying and moving memory. Okay. Thank you, Jonathan, for your answer. Okay, then just a heads up. I was running all these notebooks that we passed today. All of them were open, and then the memory here, I don't know if you noticed, was almost full. And Tim just give me the alert. And if you have the same situation, you can come here and shut down all the kernels, so your memory is going to decrease. And okay, so at this point we can move to the last thing that we're going to see today, which is Dask array. Remember that the Dask, besides the Dask delay, it extends NumPy and Python with some data collections. The one we're going to see today is Dask array, that is a version of NumPy arrays done for written for distributed workloads and for data larger than memory. So what is a Dask array? Dask array, you can deal with it similar to a NumPy array, but in the background, in the backend, all the operations are divided in chunks. And effectively, a Dask array is a set of NumPy arrays. So it's divided in chunks, and each of them is a NumPy array. So these NumPy arrays, they are not, since it is for larger than memory data, they not all add in memory at the same time. That's the advantage of having the chunks. They can be on the disk, or they can be on remote machines. They can be pulled from there are many ways to connect the Dask array to the data. Today we're going to see from disk, from HDF5 objects. And Dask array, most of the functions of NumPy are re-implemented here in this chunk-based algorithms. And one point that is very important is for small sizes, the Dask array is not a replacement for NumPy, because you can add some overhead for some of the functions. Okay, you should only use it in the case that you need to deal with a lot of data that NumPy cannot handle. Okay. So how this works in the backend, this Dask array have this delayed task execution that we saw before, very similar to what we did by hand when we split our data in chunks in the previous notebook. But this one, it will do all this kind of stuff automatically for you, so it's hidden from the user. And the blockwise, these chunk algorithms are run in graphs, same as the delay. And for instance, let's consider this one. This is a fake graph that I created to show you. It's not the real work, but more or less it represents the idea. So we have in Dask 3 states when a node, that's an operation, is waiting or is computing, or is allocated or has allocated memory, or when it finished, that the memory is freed. So let's say that this one we have the array that is reading from data. We have from disk. We say in practice we see how we do it later, but let's say that we say this array is reading from disk. When it runs, it loads memory on demand to the RAM, and let's say for this operation, it needs to divide it in 5 chunks. and then continue like this. No, these five chunks, they don't fit in memory in this case. No, let's say they don't fit in memory. They can fit only 3. In that case, Dask will run all these 3, and when these 3 things are done computing, it will pass it to the next chunk. It will get some output from it, and the memory is going to be free. So these things are already computed, and the memory was released. Now you have a space to do more calculations because all these 3 were released. Okay, you can do now. Dask can do these 2. It will do the same thing. When it's done, it creates an output. It passes to another point of the graph, and it frees this point. And this connection here, since it doesn't need to read more data, this is free too. Then these 2, they're going to be run. Finally gives you some output, frees the memory, and frees the whole thing, and then the execution is done. Okay? Some questions about it? Okay, then if not, let's go to 03 Dask array and 04, where we start with 03, and let's play a bit with Dask arrays. No questions? Okay. So in this one, we're going to run it together. We're going to create some Dask array in memory. It's not a real use case. It's just to introduce you. So here we say we create this one. It's 2000 by 2000 with chunks of size 500 by 500. So when you put X in the notebook, you get something graphical like this. And then it tells you the size of the array, the shape, how many tasks the task is related to the graph it's going to use. It's going to use the type. Then the same thing for the chunk. How many megabytes takes, the size, how many chunks are there, and the type that we know already that every of the chunks is a NumPy array. Okay, and this is somebody was asking a question about knowing the shape of a result before doing the calculation. In this case, in here, in most of the operations, depends really your workflow, but in many cases, if where you build this truly Dask graph, you can have this opportunity to see the shape of the output before it is computed. In this case, when we run this one, there is not memory allocated or anything. We're just declaring that X is this array, but this array doesn't exist in memory at this point. Okay, and now we can do like NumPy things. We can do the mean of the array, and we pass it to Y, and Y we visualize. I'm sorry, I'm in the wrong kernel. And you see that it's a more complicated graph than we saw before, but those are the 16 chunks that we were talking about. So there are some operations in chunks. You see the size, the indices of the chunks. This passed to something else, smaller, and then to something else, and at the end you get the final value. Okay, which is the mean, which is what you want. And now this is some examples here with a bigger array. Now we have 2000, dimension 2000. Let's compute the mean. We get 585 milliseconds, and do the same thing with NumPy. Okay, here we got some speed up with Dask. That's very good. Again, it's for data when you're using big arrays, okay? And now let's try with dimension 200, something small. We got here 88 milliseconds, and here we got microseconds, okay? So in this case, this is not worth to use Dask because it's just adding overhead for this amount of data, okay? It's faster with NumPy. And now let's consider another operation. This was mean. This is a very simple operation. It's just summing. So now let's do a dot product with NumPy 2000 by 2000. Meanwhile, I'm going to check if there are questions. If you look here, in the memory is increasing because so this is a large size. So we got 42 seconds with NumPy. And now let's have a look, the same thing with Dask. We're going to use 500 by 500 chunks. But you see, this is quick. No, nothing was, there's no data memory. Remember this one, it takes no time, okay? Here there is nothing is done. You just declare the operation, just immediate. Now we can visualize it. This is the operation. It's a very complicated graph, okay? Because it's chunk-wise. And now let's compute. Okay, this is going to take some time. I'm going to give you until 3 minutes more. And then if you want to play a bit with your notebook while this thing is running. If there are some questions, please type it on the chat. Oh, sorry, I was talking mute. Here we are over three minutes, and it didn't finish, so I just stop it. And the reason is that NumPy, Dask is not a replacement for NumPy. It's just simply that. Here, the thing with NumPy is very slow. It takes almost a minute, but it can be handled in memory. So in that case, Dask is not completely, it's not essential. No, Dask is when the data doesn't fit in memory. And you see here the complexity of this graph, it will take more time. So here it didn't happen because mean is a simple graph. No. So the main point here with this example is that use Dask only when it is necessary. Okay, some things are going to be simpler, but complicated stuff, you should use it only when the data is large enough, and it's worth to wait all that because there is no way to do it with NumPy. Okay, and there is a question here. You are muted. Yes, thank you. And wait, I didn't understand. Why is Dask slow? Dask array slow before even doing compute? Just from the allocation of memory. Did I answer the question? What I said about the complexity of the graph and is the answer your question, or the question is something different? Okay, good. So it is very slow because the graph is very complicated. The only reason why you want to run this thing dot with Dask is if for some reason that in general I don't think it's a practical thing to run dot with such a big array. But in general, you want to run a complicated thing with Dask only if the data requires it. Okay. So I think we can give I can give a couple of minutes until 25 if you want to see a bit the notebook and play a bit with Dask array, and then we go to the last notebook. Are there more questions? Okay, then let's move on to the next notebook, and that's 104 Dask arrays from file. So here we have a set of files, HDF5 files, that they are from weather data. I think it's temperature, global weather data, and each of them has data for a single day. So this is January 2014, and there are 31 files. And they take about 576 megabytes, in total 16 gigabytes. So this one is not larger than the memory of Python, but it's larger than it can be larger than a laptop or something, the memory of a laptop. And the good thing of this exercise is you can run it in your laptop and you can run it on Python. Okay, and even you can add more months here, more days, and the thing will scale. Okay, so we have this 16 gigabytes of file, and we want to do some operations with it, very simple things. First, we open it. They are in Scratch. All of you should be able to access it. File name is not, that's nice. And so here, when we run this one, we are using H5Py file to open them, and this one doesn't load anything in memory. It kind of declare or connects this list of objects, or every of these objects, to the file, but there is no loading. Okay. And we can see the shape, for instance, but we don't have anything loaded. And we want to, let's make a plot. Until this point, so we haven't used Dask or anything. We're going to plot one of the days, day 0, and we're going to skip every 4 points because to make the plot easier. Okay. So here you see this is the world, and this is distribution of temperature. Okay. So this is a single day. Now, in general, in weather forecast or many things, we need operations that depends on the whole history. Here, for instance, maybe we are interested in seeing the average temperature over all the days. And this is the kind of stuff that we can do very simple, very easily with Dask array. For that, we create a Dask array using this function that I'm introducing now from array, and we pass the list of HDF5 files. Okay, so this set is the list of files. We pass it to Dask array, and we create a list of these Dask arrays connected to the files. So the Dask array is connected to the HDF5 object, and the HDF5 object to the disk. Okay, here we set the chunks, and we see it's fine, 31. This is a list, and this list of arrays we can stack them on a single array, and we use Dask array. And here we have this information similar to what we saw before. So what we have here, we have array 16.4 gigabytes. So the total thing. Again, this is not in memory. This is if you see the memory, this memory is from from the previous notebook. Okay, it's not in memory, and the shape is 31 by the shape of each of them. So 31, the number of days, and they are repeated. They have also the same shape here, And then the chunks is one chunk in this direction, sorry, size 1 in this direction, and 500 in this direction. Okay. Number of tasks, number of chunks, NumPy array float 64. If we open one of this first one of the arrays of the stack, is one of this one, which is what we saw here, and each of them takes 500 something megabytes. Okay. And until this point, again, you are seeing all these numbers, but nothing is in memory, it's just declared. Now we want to compute the mean over axis 0. Axis 0 is this one. So it's the mean over the days of the whole array. We do like this. And we are going to plot this mean. Until this point, mean is not run, okay? We're going to pass it to matplotlib. Here we can do mean compute and pass to matplotlib, or can pass it directly, because matplotlib, since it is expecting a NumPy, Dask will realize that it needs to compute it, to give it to matplotlib. Okay, so we do like this. If you have a look here at the memory, so the whole thing takes 16 gigabytes, but our memory is not even close to that, and we already have the plot. Okay, so imagine if we are doing instead of 16 gigabytes, we're doing 120 in our 64 gigabytes RAM nodes. This also can be done without no problem, because you don't need that memory with Dask. Another here, for instance, we can compute again the difference between one day, day one, and the mean. And it's pretty much the same. So if you do this with NumPy, in this case, probably you can do it, because the memory is enough. But probably it's going to be slower, considering that the function that you're running is, the operation that you're running is very simple. But the main point, the main drawback of doing it with NumPy for this amount of data is that the memory, we're going to consume a lot of memory, because NumPy will try to open to load the whole thing in memory. When I was preparing this, I did it on my laptop. I ran this one in my laptop, and then I had the idea of doing it in NumPy. And well, I almost have to turn off my computer, because I started to paste and the memory was completely full, and writing in disk. Anyway, it was horrible. But this one, you can take it like this and run it in your laptop without no problem. So, questions?